me, I'm I'm a PhD student in the aeronautics team at Untitled France. And today I'm going to talk to you about clustering technique we've developed in Faro to recover for conceptual clustering. So first, I'm going to explain what is clustering, what is the concept, how we gather all of that to make our conceptual cluster, the approach, and our issues. So first, clustering. Clustering is just a way to gather elements according to parameters. Basically, when you gather books according to their topic, you are doing clustering, where books are the elements and topics is the parameter according to which you are gathering these books. So in this example, I have a book with a red topic, and I found also the books with this red topic, and there's books with other blue and yellow, orange. And of course, clustering it's not only for the books, but also for computer science. I'm using it for reverse engineering, re-engineering, and there is other application. Then, concept. What we call a conceptual cluster, it's a cluster resulting from a clustering technique where the parameter is a concept. Concept is something that has meaning for us, human, but not really for robot or computer, or at least until we give them feelings. And techniques have been developed to find concepts in a software. Applications are multiple, like identifying which part of the code has to be tested for a specific feature, or to trace the feature in code. You can find an example of these techniques in the feature location field, for example. So that was quick, but now how we use it to have just a conceptual cluster. First, we have a generic iteration where we use an extractive graph. It's quite usual. For each iteration, this extractive graph has to be defined, the nodes have to be defined, as well as the connections. For example, here I have the nodes are the packages, and the connections are the imports. Connections here are dirty edges from one package to another. It means that, for example, here we have package E that imports package E. This is the first step. Second step, we asked to the engineers to select what we call the kernel for the cluster. It's just we don't want to use some complex algorithm to compute everything automatically. We know that the engineers have some information, they have some knowledge about the software, so we want to use this kind of knowledge. And we can't just plug their brain on the computer, so they have to give us some information. So here, I asked them to select three kernels. A kernel can have multiple nodes, but also one. For example, A and D are just one kernel for one node for one kernel, and C and H are two nodes for one kernel. Then we try to navigate the graph from the kernel. So just starting with the node A, kernel red, we're gonna just navigate the graph to go to nodes E, B, and C. And for each node, we have a function to decide whether we allocate the nodes to this cluster or not. Here, it's really stupid. I just take every node I navigated and put it in the cluster. But I can say maybe C is not a good is not good for this cluster, so I will not put C in my cluster. It depends on what kind of allocation function you are using. Then I just keep going and allocate every node to my cluster according to the allocation function. There is a difference between what we are doing here, comparing to traditional clustering technique. Because in a traditional clustering technique, you should normally define a similarity metric or distance between the nodes, and then you compute the distance between every node of the graph, or similarity. We have usually the similarity metric or distance is up to the engineer that implements the clustering technique. Here we don't use distance or similarity, we just try to use what the engineers are doing, because when an engineer is doing a reverse engineering of a software, they are not trying to compute kind of a distance in their brain. They don't have any formula for distance or similarity. So they're using something else, like, for example, just going through the dependencies between the nodes. That was only just a generic iteration. So now how we use it really? We are using it in an iterative approach. Why iterative? Because we consider that we have a hierarchy of clusters. It depends, of course it depends on what you are targeting, but in our case we have this hierarchy of clusters. And the idea is to start with the biggest clusters, and then to try to refine the cluster. So the first step is to go to start with the packages. This is specific to the language I was working with. It's ADA, but you can have packages, classes, methods. Here we just have packages and subprograms, and some other kind of behavioral entities, but it's basically subprograms. So we're starting with the packages, and we try to allocate with our method, our generic iteration, the packages to the biggest cluster, cluster 1, 2, 3. Then we have big cluster with packages, and inside every packages there is subprograms. So now, with the subprograms, we are trying to refine the clusters we had before. So instead of trying to allocate the subprograms to cluster 1 to 3, we try to allocate the subprograms to cluster 1, 1, 1, 2, 1, 3, and so on. Using also the generic iteration, but an instance. This is the real difference. There is two different instances. One for the first part with the packages, and another one for the second part with the subprograms. So in each instance you have to define what I presented before. I mean, the nodes, the relationships between the nodes, the kernel, the nodes in the kernel, and the allocation function. But I'm pretty sure you've seen some problem in the graph I presented before, and we consider this problem. For example, in this graph, you've seen some dependencies, and it can occur. We are using static methods to extract the graph, so you can have some kind of cyclic dependencies. We are targeting these cyclic dependencies by using a simple way. We just keep track of all the nodes that have been navigated. If you try to navigate in a node, for example here, I've navigated from A to B to C, B to E, and then from E to G, from G to F, then F to E, but I've already been on E. So it's useless to go again on E and try to navigate to these outgoing nodes. So since you keep tracking, you're keeping track of the nodes, you don't need you don't have the problem of cyclic dependencies, because you just forgot about you don't go to the node where you have been before. There is another problem. With this example, I have two columns, A, D. and C will be navigated from A and from D. So this is an issue we had, especially in the second instance with the subprograms. In the first instance, we had some of them, but the engineers asked us to create what we call conflict resolution functions. So these conflict resolution functions should resolve your conflict. This is a conflict. So C will be either on A or on D. It's not a or, but it's or. You can't be in A and in D for the first iteration. In the second iteration, it's something different because they wanted to have this information. C will be in A and in D. There is some meaning of that. If a subprogram is in two clusters, it means for them that we need to cut this subprogram, to split it in different pieces. So for the first part, we created this conflict resolution function, but for the second part, we just keep the information about where the nodes have been allocated, especially if it's in multiple clusters. But what now about numbers? For the first instance, we compared our approach with what they have done on the manual side, and we got a precision pretty high. Precision, I don't know if everybody is used to that, but precision is just if you pick a result from your approach, it's the probability that this result is good. And the recall is if you pick a result from your oracle, the manual approach in our case, it's the probability that you will have the same result somewhere else, same good result somewhere else in your approach. So for the precision, we have a pretty high precision, a recall correct. It's pretty high also for the first instance. We had some problems actually with the second instance because the precision is quite low, the recall is really low, but we have some ideas on how to improve this second instance, and this idea is what we are going to do. Actually, we're going to not just use an expected graph, but also the cases in the methods, because some methods have what we call the switch case when you have a lot of I think all the languages have this kind of structures, and since we are trying to recover the features, the concept inside the software, this kind of structure, the case when, will can give you information on I go to this case because of this feature, I go to this case because of this feature. So the idea is to find every method where this kind of case when, not in all the application, but only in one big cluster. It's stupid to do it just for all the application. I will have a lot of different methods, too much actually, too many. And with the case when, try to allocate the when in a cluster. So this is what we are going to try on our case. We have already tried some stuff. For now, we don't have any good results, any relevant results, so I will not present the result today. But this is what we are going to do. So this is the end of my presentation. Thank you for your attention.
Yes, we do not have time for questions. So
Sorry.
if you have questions, you can meet with